This presentation uses the conventional carbon dioxide bicarbonate relationship. This is in keeping with what one finds in most anesthesia texts. Those interested in the Stewart approach should read Miller's Anesthesia and Dr. Story's excellent review. Classification and calculation rely on the carbon dioxide bicarbonate relationship. Looking at the chemical formula, we recognize carbon dioxide as a weak acid and bicarbonate as its conjugate base. As with any weak acid-base pair, we can precisely calculate their ratios at a given pH. Remember the pKa. This is the pH at which there is a 50-50 mix of an acid and its conjugate base. Carbon dioxide and bicarbonate's pKa is 6.1. At a pH of 6.1, your blood would contain equal amounts of carbon dioxide and bicarbonate. The Henderson-Hasselbalch equation defines the relationship between pH, pKa, and acid-base pairs. On the left we have pH. pH equals the pKa plus the logarithm of base divided by acid. Note that the equation has only three unknowns. This means that given any two values, we can calculate the third value. On a blood gas, both carbon dioxide and pH are measured. Bicarbonate is calculated. The equation tells us two things. The equation tells us that the ratio between acid and base matters. Let's put real numbers into it. Insert bicarbonate's pKa of 6.1. We add carbon dioxide solubility of 0.03. Assume a perfectly normal patient. You have a bicarbonate of 24 and a carbon dioxide of 40. Plug the numbers into a calculator and arrive at 6.1 plus 1.3, which equals a pH of 7.4. Now consider a chronic COPD patient whose carbon dioxide sits at 60 with a bicarbonate of 36. Plug these numbers into your calculator and see what happens. Again, we have 6.1 plus 1.3 and a pH of 7.4. The equation tells us that the ratio between acid and base matters. Unfortunately, Henderson-Hasselbalch fails to account for other acid-base pairs. We know that sodium, chloride, lactate, albumin, phosphate, and other substances directly change pH. Further, studies show that patients frequently have low chloride levels that normalize pH during lactic acidosis. 20% of some patient groups have a normal pH, carbon dioxide, and bicarbonate values during significant lactic acidosis. If you're concerned about hyperperfusion, check a lactate along with the blood gas. With this background in place, let's explore ABG analysis. We define a normal ABG as having a pH of 7.35 to 7.45, carbon dioxide of 35 to 45 millimeters mercury, bicarbonate 22 to 26 milliequivalents per liter, base excess of plus to minus 2, and a lactate of 0.7 to 2.1 millimoles per liter. All anesthesia texts recommend a methodical approach to blood gas analysis. The approach listed here is the narrator's hybrid, and I recommend careful study before adopting it. First, assess both the patient and look at the initial blood gas. Make sure that the pH of 6.7 agrees with the clinical picture and is not a laboratory error. Take immediate action if indicated. Determine the direction of pH change and use this direction to identify primary processes. Assess the amount and chronicity of compensation. Evaluate electrolytes, albumin, and the need for lactate measurement. Finally, compare your analysis against the clinical picture. The pH direction identifies the primary disorder. A pH below 7.40 signals acidosis as the primary disorder. A pH above 7.40 indicates alkalosis as the primary disorder. The body's compensation mechanisms never overcompensate. They merely bring the pH back to a normal range. So if respiratory acidosis drops the pH below 7.35, metabolic compensation will not overcorrect to a pH above 7.40. Unfortunately, medical treatments may overcorrect and complicate your assessment. Classification quickly and efficiently identifies simple acid-base disorders. This three-column model can be found in Morgan's Clinical Anesthesiology and other texts. In the left column are potential disorders. Based on the pH direction, identify primary acidosis or alkalosis. Next, assess the carbon dioxide or bicarbonate to identify the primary change. If the primary change was increased carbon dioxide, bicarbonate should be elevated to signify compensation. If carbon dioxide is high and bicarbonate low, the disorder would be a mixed acidosis. ABG number 1 has a pH of 7.35, carbon dioxide of 55, bicarbonate of 29, and base excess of positive 3.9. With a pH below 7.40, the primary disorder must be acidosis. Carbon dioxide is elevated, leading to the diagnosis of respiratory acidosis. Bicarbonate is elevated, showing a compensatory response. Because the pH has been normalized to 7.35 or greater, this patient has respiratory acidosis with metabolic compensation. The ABG is a bit troubling because we know that metabolic compensation should nearly normalize the pH. This raises the suspicion of chronic respiratory acidosis combined with an acute respiratory or even metabolic event. ABG number 2 has a pH of 7.31, CO2 of 27, bicarbonate of 13, base excess of negative 11.7. The pH clearly shows acidosis. Carbon dioxide is low, ruling out respiratory acidosis. The bicarbonate of 13 indicates metabolic acidosis. With a carbon dioxide of 27, the patient is attempting respiratory compensation. However, since the pH remains less than 7.35, the compensation is incomplete. Therefore, we diagnose metabolic acidosis with incomplete respiratory compensation. ABG number 3 has a pH of 7.24, carbon dioxide of 50, bicarbonate of 21, and base excess of negative 5.7. Following our boxes, we see that this patient has combined respiratory and metabolic acidosis. How might you treat this patient? Administrating bicarbonate would significantly raise carbon dioxide levels and worsen the respiratory acidosis. Bicarbonate should not be given without first improving the ventilation. Assuming that you can normalize the carbon dioxide level to 40, what pH will the patient have? It becomes apparent that more than boxes are needed when choosing treatment. These rules of thumb come from Barish. For every 10 increase in carbon dioxide, the pH drops by 0.05 units. Conversely, for every 10 decrease in carbon dioxide, the pH rises by 0.1 units. Some techs and clinicians simplify and combine the ratios. For every 10 change in carbon dioxide, the pH changes by 0.07 units. Using the numbers from Barish, we could predict that decreasing carbon dioxide from 50 to 40 would increase the pH by 0.1 units. This should raise the pH from 7.24 to 7.34. The rules of thumb give us the knowledge that fixing or controlling the patient's ventilation will adequately normalize pH. Some of you may wonder why I chose 0.1 rather than 0.05. Click the Explore button to find out why. You may remember this picture from an earlier presentation. The black line follows the actual logarithmic change in proton concentration versus pH. Because the proton concentration changes logarithmically with respect to pH, the line is curved. Starting at a pH of 7.4, follow the curve's leftward path. It gets increasingly steep. Going to the right from a pH of 7.4, the line begins to flatten. This is why Barish provides two ratios. One is for the steep and the other for the flat portion of the curve. One could argue that for any pH less than 7.40, a 0.05 to 10 relationship should be used. However, this would probably confuse lots of people. Now let's look at the 0.07 line in green. While easier to remember, it is accurate over a shorter distance. Both ways of estimating are good, as long as one remembers the associated compromise. The rules of thumb worked on the respiratory side of our acid-base equation. The base excess formula uses bicarbonate, or the metabolic side. It empowers us to quantify the disorder and calculate a bicarbonate dose. The base excess is the number of milliequivalents of bicarbonate needed per liter of extracellular fluid to normalize the pH. This assumes both a normal temperature and carbon dioxide level. The bicarbonate dose required to completely normalize the pH is 0.3 times the patient's weight in kilograms times the base excess, where 0.3 is bicarbonate's volume of distribution. Do not give more than 1/2 of the calculated dose. Several formulas exist for differentiating acute versus chronic respiratory acidosis. Barish states that for every 10 rise in carbon dioxide, bicarbonate acutely rises by 1. In chronic disorders, bicarbonate rises 4 to 5 for every 10 rise in carbon dioxide. Let's apply these numbers to our first ABG. The patient had a carbon dioxide of 55 and a bicarbonate of 29. In acute respiratory acidosis, bicarbonate should rise by 1 for every 10 rise in carbon dioxide. Since 15 is 1.5 units of 10, we multiply 1.5 by 1. Add this value to a normal bicarbonate of 24 and arrive at 25.5. In acute respiratory acidosis, the bicarbonate should be about 25.5. In chronic respiratory acidosis, the bicarbonate should rise by at least 4 milliequivalents for every 10 rise in carbon dioxide. With a carbon dioxide 15 points above normal, the bicarbonate should have risen by at least 6 milliequivalents to a level of 30. The patient's actual level of 29, therefore, indicates a combination of acute and chronic disorders. At this point, you may be wondering why anyone would calculate this when they could classify disorders, calculate only when necessary, and use the base excess for quantification. The answer is anything but simple. The 1960s saw heated debate between prominent scientists in Copenhagen and Boston. The Americans advocated using 6 rules of thumb, while the Danes promoted an approach using the base excess. The debate became so heated that we feel its effects in 2011. According to a review by Dr. Story, the strength of the debate is why some current texts do not mention the base excess. Try to find the base excess in the 6th edition of Barish's Clinical Anesthesia. If this type of thing interests you, Dr. Story's article is a great starting point. The ABG listed here can be found in Miller and came from a patient needing urgent abdominal exploration. This ABG appears nearly textbook normal. However, the patient's chemistry values show someone at serious risk of death. 2 questions arise. How can the ABG be normal with a lactate of 6? Also, how common is this scenario? An excellent retrospective study appeared in 2008 and has been supported by later research. According to this study, 20% of surgical and trauma patients had both normal ABGs and lactate levels greater than 4. According to the law of electroneutrality, the number of positive and negative charges within a solution must be equal. This picture shows a balance scale with common cations and anions on each side. What happens when lactate levels acutely rise? Something must provide balance. In the short term, hydrogen and hydroxide ion levels rebalance the scale. Water donates hydrogen ions into solution and pulls hydroxide ions out of solution. It is important to note that the water in our patients provides a near limitless supply of hydrogen ions. Things get tricky as lactate levels rise in the presence of low albumin or chloride levels. This mechanism of multiple derangements is why 20% of patients had normal ABG values amidst significant lactic acidosis. Miller provides these numbers to assist with the extremely complex patient. Note that elevated sodium causes alkalosis. Conversely, low sodium creates acidosis. The balance between sodium and chloride is important as the 2 effects may cancel each other. Note that albumin is a weak acid. In the patient several slides back, low albumin levels hid the lactate of 6. Thanks to Miller, those who memorize this slide can quantify the impact of individual chemistry values. Using the law of electroneutrality, the anion gap subtracts commonly measured anions from cations. Chemistry values do not measure a number of negatively charged molecules. This results in a predictable anion gap. However, a growing anion gap indicates the presence of unmeasured anions, such as lactate. Several formulas and corrections of the gap exist. However, literature questions the anion gap's value. The anion gap may fail 50% of the time in acute patients. Because of this, one should consider drawing lactate levels whenever hypoperfusion is suspected. The process of analyzing acid-base disturbances is quite complex. Because of this, approach the ABG in a methodical fashion. Electrolytes should be analyzed with close attention paid to sodium, chloride, and albumin. At a minimum, one should understand the influences caused by sodium, chloride, and albumin disturbances. The complexity of your patients will determine the value of calculation. Finally, while the ability to calculate aids in patient assessment, acid-base disturbances humble everyone. Page 2565 of Miller's 7th edition states, "It is probable that no single number will ever allow investigators to make sense of complex acid-base disturbances. No calculator or calculation will ever replace the vigilant, seasoned clinician."